The length of a river, a nation's population, the amount on an accounting ledger. 3 in 10 of the world's numbers start with 1. It is no coincidence. In 1881, the American astronomer Simon Newcomb brought up a curious observation in a short paper. Back then, scientists thumbed through thick books of numbers called log tables to speed up multiplication. But Newcomb pointed out something curious. The front pages of those books were worn noticeably darker than the rest. He wrote this in his paper. The front of a log table holds numbers starting with 1, and the back holds numbers starting with 9. That the pages wore out from the front means people looked up numbers starting with 1 far more often. But think about it, and it's strange. There are 9 digits from 1 to 9, so if things were fair, each should turn up 1 and 9 of the time, roughly 11% each. But reality is nothing like that. River lengths, national populations, stock prices, even the amounts on accounting ledgers. Count the leading digits, and numbers starting with 1 dominate at about 30%, while those starting with 9 are under 5%. This strange skew has a name. This is no idle quiz. With no hard math at all, just by counting and plotting the leading digit, let's uncover what this lie detector really is. So let's first see in a picture exactly what Benford's law says. The law's claim is just one sentence. Count the leading digit of numbers scraped from anywhere, and the smaller the digit, the more often it shows up. And in remarkably steady proportions, the leading digit is 1 about 30% of the time, and 2 about 18% of the time. It falls as the digit grows, and by 9 it's under 5%. If things were fair, 1 through 9 would all sit flat at 11.1%. The real shape is a steep downhill staircase. Let's plot it ourselves. Here is the downhill staircase. 1 is highest at 30.1%, and step by step it drops until 9 reaches just 4.6%. So numbers starting with 1 are a full 6.6 times as common as those starting with 9. This ratio wasn't set arbitrarily. The probability that the leading digit is some digit d is pinned down neatly by this single line. Read aloud, it goes like this. Take 1 plus 1 over d and then take the log of it. This is essentially the only formula in the whole piece, and you don't even need to memorize it. Just remember one thing, there's a logarithm sitting right here. In Chapter 3, why it has to be a logarithm becomes the key to the entire mystery. Of course you'll be skeptical. Could a single formula really match the actual numbers of the real world? So in the next chapter, we'll bring in groups of numbers that have nothing to do with one another, and count their leading digits ourselves. The person who made this law famous was someone else entirely. In 1938, it was Frank Benford, a physicist at General Electric in the United States. He rediscovered, completely independently, the observation Newcomb had left half a century earlier, without knowing about it at all. Look at the numbers he counted one by hand. Their sources are wildly varied. 20,229 numbers in all, and every single one of them traced out that same downhill staircase. A mischievous footnote of history, Newcomb discovered it first, but the name went to Benford some 50 years later. There's even a name for this. When something gets named after the person who made it famous, Stigler's Law. Let's reproduce what Benford did. We've prepared 4 groups of numbers with completely different characters. I counted the leading digit of each of the 4. Laid out on a single chart, here's the result. All 4 groups, as if by agreement, draw the very same downhill staircase, and yet they have nothing to do with one another. Let's set the actual share of leading digit 1 right next to the theoretical value of 30.1%. Fibonacci and powers of 2 aren't just roughly close. It's a theorem proven to come out exactly this way. In 1977, the statistician Percy Diaconis and others proved it rigorously. The overlap with the dashed line is the evidence. Real measured data, on the other hand, drifts off a little. The one of the physical constants rises a touch higher than theory. Now the question we're most curious about. Why on earth does one win by this much? Why 1 of all digits? The answer hides in the world of multiplication. The secret hides in that logarithm we met in Chapter 1. Don't be scared. Just one thing. Picture a log ruler whose tick marks grow narrower and narrower. Why does this matter? Because the way nature grows numbers follows exactly this log ruler. On the left is the log ruler, one span from 1 to 10 stretched all the way out. The land one occupies from 1 to 2 is the widest at 30% of the whole. By contrast, the territory of 9 is a narrow alley, only 5%. This very territory width is exactly the Benford probability. Why do the world's numbers scatter evenly across the log ruler? The key is multiplication. In nature, quantities grow not by addition but by multiplication. On the right is a simulation that grew 1 by compound growth over 20,000 steps. The time the leading digit stays at 1 is the longest, about 30%. The reason is simple. For 101 to become 201 takes 2 times. For 901 to reach 1001, 1.1 times is enough. Growing at the same rate, escaping the 1 zone takes more than 6 times as long as escaping the 9 zone. But this multiplication magic holds one more, deeper secret. Whether you measure a river in miles or kilometers, whether you record a ledger in $1 or dollars, the staircase appears just the same. Changing the units means multiplying every number by the same factor. On the log ruler, it merely slides everything sideways. The cell widths stay the same. This very property, being unswayed by units, is the deepest reason Benford pops up, as if on cue across all kinds of data. Numbers cannot lie. Now it's time to see how to catch fraud. It's time for this 30% law to turn detective. The core is almost absurdly simple. Why is that? When people invent plausible amounts in their heads, they scatter 1 through 9 evenly. On top of that, embezzlers often write in amounts just below the approval threshold. In 1990s Arizona, a state official trying to siphon off about $2 million in public funds fell right into this trap. The 23 forged checks he made mostly started with 7, 8, or 9. The numbers, in effect, turned him in. This is exactly the test accountants run. They pull just the leading digit from every amount. We plotted an honest ledger and a doctored ledger side by side. The honest ledger on the left hugs the yellow staircase, while on the right, 8 and 9 rise up like towers. Let's confirm it with the numbers. The difference shows at a glance. What we just saw is the most basic test. A clever fabricator tunes the leading digit to land between 1 and 3. So the weapon forensic auditors love is one level deeper, the first 2 digits test. The same formula applies to the first 2 digits. Only now it's 90 bins instead of 9. People have a habit of rounding the last digit to 0 or 5 so it pops out as comb pattern spikes. Tampering that looked clean on the first digit gets exposed once you add one more digit. The one who honed these tests into forensic accounting practice is the accountant Mark Nigrini. In the 1990s, he laid out how to use Benford's law to catch tax evasion and accounting fraud. An entire country has been caught, too. In 2011, 4 economists examined Europe's fiscal statistics. It was right before the European debt crisis, and Greece later did in fact admit to cooking its statistics. By now it sounds like an all-purpose detector, right? But, and this part really matters, it isn't. A broken staircase doesn't by itself prove fraud. Honest data can deviate just as easily. There's also the opposite failure. The returns of Bernie Madoff, the biggest Ponzi schemer in history, actually fit Benford well. Conversely, fraud buried in a huge dataset can be too small to catch. So when does this law work and when does it not? Not knowing this can leave you badly embarrassed. In fact, it once blew up in a big way. The most famous mishap erupted right after the 2020 US presidential election. A graph spread all over the internet. But statisticians shook their heads in unison. The problem was not election fraud. You shouldn't apply Benford to precinct vote counts in the first place. Benford only holds when the numbers spread out broadly across many orders of magnitude. But a single precinct's vote count is at most a few hundred to a few thousand votes. The range is far too narrow. The criticism that a leading digit test on election data is no better than a coin flip is close to the consensus. Here the conditions for it to work come into view. Benford favors numbers that spread broadly across many orders of magnitude and grow by multiplication. Conversely, it doesn't work on numbers like these. narrow-range values, human-assigned numbers, and pure randomness. Phone numbers and receipt numbers aren't measured values but labels assigned by people, so they have nothing to do with nature's multiplication. So whenever someone brandishes this law at you, ask first. With that answer in hand, we now move to the final chapter. Finally, the story of the fingerprint that numbers leave behind for us. Let's return to those worn-out pages. What Newcomb saw was not a smudge but a fingerprint. As long as nature shapes numbers by multiplication, whether rivers, stock prices, or ledgers, the leading digit carries the fingerprint one about 30% of the time. Try to forge that fingerprint the moment you invent plausible-looking numbers in your head, and you leave a mark that's out of line. Benford's law is the magnifying glass that reads exactly that deviation. Intriguingly, this magnifying glass has crossed beyond paper ledgers into the world of pixels. So in the 2020s, researchers applied the same idea to spotting fake images made by JNs and deepfakes. Of course, even this isn't foolproof. Recompression blurs the signal, and there are techniques that restore the fingerprint to dodge the test. A law that began with worn book pages over 80 years ago now stands at the front line of spotting AI-made fakes. Next time you come across a document full of statistics just for fun, count the leading digits. If there are unusually many ones, you've just spotted the world's fingerprint. And if there are strangely few ones, well, those numbers might just be something someone made up. If you enjoyed today's journey, support us with a subscribe and a like. See you at ELLS Lab for the next Odyssey.